Okay, for what we have in the case of number 45, and this one has a bit of an added twist to it in terms of trying to determine what is going on. And we have posed, supposing a population P of rodents satisfies the differential equation dP over dt, or the change in population with respect to the change in time, is equal to the product of the proportional constant k times the square of the population. And we have initially there are p of 0 is equal to 2 rodents, and their number is increasing at the rate of dp over dt is equal to 1 rodent per month as soon as the population reaches 10 rodents. And we have under the conditions, how long will it take for this population to grow to 100 rodents, and subsequently how long will it take to grow to 1,000. And we have also posed the question, what is happening here? Okay, so we have for the differential equation, so we have dp over dt is equal to kp squared, and setting things up whereupon we can express in terms of the population p. So in this setup, we can separate the variables. Okay, so we'll simultaneously divide by the square of p and multiply by the differential dt. Okay, so we have dp all over p squared is equal to dt, and upon separating, we can integrate. And just going back, okay, so for the reciprocal of the square root of p, we can apply the power property of integration. Okay, so for the reciprocal of the square root of p dp, we can write this as p to the negative 2 dp. And what's going to happen here, okay, we're going to have, with the power property, we'll have the negative of p to the negative 1 followed by the constant, whereas in the rewrite have the negative of the reciprocal of p followed by the constant. So just taking what we have here, so you have negative 1 over p Okay, for what we have in number 45, okay, we have posed the situation here where we have, suppose a population P of rodents satisfies the differential equation dP over dt is equal to kp squared. And we have initially there are P of 0 is equal to 2 rodents, and their number is increasing at the rate of dP over dt is equal to 1 rodent per month whenever the population reaches 10 rodents. And under the conditions, how long will it take for this population to grow to 100 rodents and then to 1,000? And we have finally what is happening here. Okay, so we have with the proposed situations. Okay, now we have in the differential equation, okay, so you have the change in population with respect to the change in time is equal to the product of the proportional constant k and the square of the population p. And here we can separate the variables. Okay? And so we can simultaneously divide by the square root of p and multiply by dt. So you have dp over p squared is equal to k dt. And upon separating, we can integrate. And just going back, okay, so we have the reciprocal p squared dp now if I had the reciprocal of p, the antiderivative will be a natural logarithm, but here I have the reciprocal of p squared, okay, and rewriting in exponential terms, so the reciprocal of p squared is going to be p to the negative 2 And for the power property of integrating, this is going to translate out to the negative of p to the negative 1, followed by the constant. And we can also say we have the negative of the reciprocal of p plus c. And just relaying this over to what we have in the following step. Okay, so antiderivative of the reciprocal of the square of p, we have negative 1 over p, and I will have the constant transported to the right hand side, and the antiderivative of k dt is going to be kt. And again, I'm just going to add the constant at that end. And what we can do now is to change the sign at both ends. So you can say we have 1 over p is equal to negative kt, and I could say minus c, but I'm just going to leave this in terms of adding. So just doing a little bit of color coding. So we can say we have 1 over p is equal to negative kt plus c, or it could be plus alpha. But we're just writing this as a constant we are adding as opposed to subtracting. And now if I write directly in terms of p, so just taking the reciprocal of both sides, okay, so rewriting in terms of p directly, if I take the reciprocal of both sides, we have that p is equal to 1 over negative kt plus c. And we have with the other situation thrown in, okay, with the added detail, again, we have that dp over dt is equal to 1 whenever we have the rodent population to reach 10. Okay, so we have simultaneously, we'll have dp over dt is equal to kp squared, and we have also dp over dt, again, is equal to 1 whenever we have 10 rodents. Okay, so dp over dt is equal to kp squared is equal to 1 when p is equal to 10. Okay, and so we have with the information, okay, so you're going to have k times the square of 10 is equal to 1, and 10 squared is 100. Multiplying by k, so you have 100k is equal to 1, and dividing by 100, okay, we have that k is equal to 0.01. And so transferring what we have now, we got this expression for p, and we have now the value of k, and putting all together. So we're going to have that p is equal to 1 over negative 0.01 t followed by the constant. Okay, so going back to the initial condition, okay, there were 2 rodents at the very start, where upon we have at time t is equal to 0, the population is equal to 2, and applying what we have for what we have in the general equation. Okay, so we have, once again, we have p of 0 is equal to 2. Again, so whenever t is 0, okay, p is equal to 2. And with t at 0, okay, so we had that 2 is equal to 1 over c. And obtaining the value of the constant, and c is going to be equal to 1/2, and I'll just go ahead and write this as a decimal. Okay, so we have with the constant at 1/2, we have for the population at any time t that is equal to 1 over negative 0.01t plus 1/2. Now, in terms of utilizing this equation, now we're looking at how long it's going to take for the population to arrive at 100 rodents. Okay, so whenever we have p equal to 100, so going back to our newfound equation, so we have for p at 100, we have 1 over negative 0.01t plus 1/2. And if I multiply both sides of the equation by the denominator, okay, just to get out of the fraction mode, so you have 100 times negative 0.01t, so there'll be a negative 1t. 100 times 0.5, so that'll be 50. So you have negative t plus 50 is equal to 1. And subtracting 50 from both ends, so we have negative t is equal to negative 49. And writing in terms of positive t, so we have that t is equal to 49. In this case, we have 49 months. So it's going to take about 4 years and 1 month for the population to increase from 2 rodents to 100 rodents. And we have for the remaining portions, we're now looking at how long it's going to take to get to 1,000 rodents. Same formula, but we now have p at 1,000. Okay, we have is equal to the reciprocal. Okay, we have negative 0.01t plus 1/2. And again, multiplying both sides of the equation by the denominator. Again, just to get out of the fraction mode. Okay, so we have 1,000 times negative 0.01t becomes negative 10t plus 500 is equal to 1. And deducting 500 from both sides, we have negative 10t is equal to negative 499. And so we have that t upon division by negative 10 is equal to 49.9 months. And there are some rather interesting dynamics. So it took over 4 years for the population to grow from 2 to 100. And after the growth to 100 rodents, it took like some 27 or 28 days to increase by another 900 rodents. And in terms of what is happening here, in terms of the dynamics with this particular equation, okay, so we have essentially as t approaches 50, you're going to have the population p to increase boundlessly.